Now what about subnet masks? I've mentioned subnet masks a few times. What is a subnet mask? What does it do? Well, a subnet mask is used to determine which part of an IP address is the network portion and which part of the address is the host portion. This allows a PC, for example, to determine whether a device that it wants to communicate with is a remote device or a local device. So here's an example. We have a PC with IP address 10.1.1.1 and another PC with an IP address of 10.1.2.1. When the PC on the left wants to forward traffic to the PC on the right with IP address 10.1.2.1, does the PC forward the traffic onto the local segment, or does it forward it to its default gateway? If these two devices are in the same subnet, they can communicate directly without the use of a default gateway. But if they're on different subnets, the PCs will forward their traffic to their default gateways, which will do the inter-VLAN routing if they're on the local LAN or local area network as an example, or route the traffic if the traffic is forwarded to a traditional router. So a layer 3 switch may do the routing between two VLANs, or a router may route the traffic between these two devices if they are in different subnets. But how would you determine if these two devices are on the same subnet or if they're on different subnets? Now I'm going to explain this in more detail in the next few minutes. But as an example, 10.1.1.1 and 10.1.2.1 are in the same subnet if they're using a /16 mask. However, if they're using a /24 mask, that means that the devices are on different subnets. So let me explain that in more detail. A network mask allows a device to determine once again which portion of the address is the host portion and which portion of the address is the network portion. This allows a local PC, as an example, to determine whether the device it wants to communicate with is on a remote network and is thus reachable via the default gateway, or if the device is on the local subnet and therefore does not require the use of a default gateway. So if PC A and PC B are in the same subnet, no default gateway is required. But if they're on different subnets, then a default gateway would typically be required to do the routing between the two PCs. So that's essentially what a network mask does. Now, as I've explained, Class A, B, and C networks have default masks, which are also known as natural masks. In a Class A address, the first octet is the network. In a Class B address, the first two octets are network, and with a Class C address, the first 3 octets are the network portion. I'll explain more complicated subnet masks in the subnetting videos, but let's first start with some simple examples. In this example, we have a Class A network that hasn't been subnetted. In a Class A network, the default mask is 255.0.0.0. So if we look at a address such as 10.1.1.1 and convert that into binary, it's going to look as follows. Now look at the following mask. 255 in binary equates to 8 binary ones. 0 in decimal equates to 8 binary zeros. So converting the mask into binary shows us that the network portion consists of contiguous ones, or continuous ones starting from the left-hand side. A 1 in binary in the network mask indicates network. A 0 in binary in the network mask indicates host. So in this example, this portion of the address is network and this portion of the address is host. Hence, this device with IP address 10.1.1.1 is on network 10.0.0.0. This is the network portion and this is the host portion. This device with IP address 10.1.1.1 is on network 10. So, when working out the network and host portions of an address, follow these two simple rules. Any address bits that have a corresponding mask bit set to 1 in binary represents the network. Any address bits that have a corresponding mask bit set to 0 represents the host. So 1 in binary means network, 0 in binary means host. So in this example, 10 is the network because there are 1s in the mask in binary, so the network ID is set to 10. Notice these octets are populated by binary zeros. That means host. So the host ID is equal to 1.1.1. So in summary, the network is 10. The host portion of the address is 1.1.1. Here's another example. Remember, any address bits that have a corresponding mask bit set to 1 in binary represents network. Any address bits that have a corresponding mask bit set to 0 in binary represent node ID. So here we've got a class A address, 1.1.1.1, but note the difference. The network mask, in this case, is 255.255.0.0. So converting 1.1.1.1 to binary gives us the following. Taking the network mask and converting that to binary gives us the following. Notice 255 equates to 8 binary 1s, which therefore means that this portion of the address is network. So the network ID is 1.1. And looking at the remaining part of the address, which is populated with binary zeros in the network mask, means that 1.1 is the host portion of the address. In other words, the network is 1.1.0.0 with a host portion of 1.1 on that network. The mask is 255.255.0.0. In this example, it's easy to see the network portion of the address because we have 255.255 in the network mask. Just be aware that things can get a lot more complicated than what we're seeing in these examples. You'll see that when we get to the subnetting videos. These two examples are simple because it's easy to recognize which portion is network and which portion is host. In the subnetting videos, I'm going to show you much more complicated examples. And in those examples, it's more difficult to determine which portion is network and which portion is host. So in summary, how does a device know whether another device is local or remote to itself? So the first thing it'll do is check the network portion of its local address and then compare that to the address of the other host. If the network portion of the address is the same, the local device knows that the other device is local to itself. If the network portion is not the same, the local device knows that the other device is remote